Today we're going to see algorithms for the first time in the class. So finally you're going to start building a toolbox. But before we see the algorithms, which is going to come towards the end of the second hour, we're going to do a bit of theory on subgradients, which will be, I think, very useful for the entire course. And again, this material you're going to see is based on Boyd's convex optimization class. So you can also see his lectures online as well. And I'm following again Matthew's suggestions about how to present the materials. So what I want to do is give you a preview of where we're trying to get by the end of the second hour. This is our target problem for the day. So we have a two-stage stochastic integer, mixed integer linear program, which means linear constraints. Some of the decisions are integer, and there is uncertainty. So we make a first stage decision, and then there's a recourse stage. The general formulation is like this. Now here it's not really apparent that this is a stochastic program, but I haven't explicitly written out the second stage, but you can abstract that some of the x's are second stage decisions, and really the source of difficulty with this problem is that because of the many scenarios, these constraints here are many. And problems with large constraint sets present difficulty. So the way to tackle the problem is to form the dual function like this. And the first question I have for you is what is the rationale behind the sign of lambda being non-negative? Rather than, for example, free or non-positive. Right. So the name of the game in relaxation is that we take an originally difficult problem and we break it up into pieces through Lagrange relaxation. And we're always looking for bounds. When we're minimizing, we're going for a lower bound. When we're maximizing, we're going for an upper bound. So in this case, note that the only constraints that get hit by a dual variable that has some sign constraint on it are the inequality constraints. Provided you give me a feasible solution to the problem, this term here is pushing the objective function over here down. So this problem is a relaxation of this problem, and the best x I can find for this problem is a lower bound for this problem, because I get rewarded in this problem for respecting the inequality constraints. In the other problem, there's no term in the objective function that rewards me for respecting the constraints, whereas here there's a negative contribution. Now, the really important practical thing that we're going to see towards the end of the class is that if given a certain lambda and a certain nu, I solve this relaxation here, I not only get the solution to this problem here, but I also get what is called a supergradient of the dual function. Geometrically, what you want to be thinking of is the following image. We have a primal optimal value, which is the objective function value of this problem here. It is what it is. We are moving around in the dual space. So we're in the space of dual variables, and we are building, we are computing this dual function here at different points. one point, for example, is here, and the value of that function at this point is this much. Another point is here, and so on. Is there a certain fact about this dual function that we know? It has a specific structure. It's a concave function. And what we're basically looking for is the best possible bound from this dual function, which happens in this case to be over here. To find this best upper bound, so to maximize this concave dual function, we would like information about what the direction of increase of this dual function is. So we get that for free, in fact. When we're solving this problem at a given point, lambda nu, we also get a supergradient of the function, which in simpler terms is a direction of increase of the function. So not only do we compute the function at a given lambda nu, but we're told which direction we have to move in the dual space to increase the dual function. And that's an important fact that we will explain. So now the idea for the rest of the lecture is to learn how to use subgradients or supergradients. So if I were looking at a concave function instead of a convex one, this direction of decrease would be called a subgradient instead of a supergradient in a concave function. So the name of the game for the rest of the lecture is to understand how we can use these vectors that are given to us at each iteration to move in a direction where we maximize this dual function. So we addressed the question of the sign and bounding a prime optimal solution. Now, do we really solve the problem by maximizing the dual function? It's just a bound. It's not like we're actually solving the problem, but often we can recover good primal feasible solutions from these solutions here. Although these are, in principle, infeasible solutions, they're close to feasible, so we can tweak them a bit and actually get feasible solutions at each iteration. And then another computationally appealing aspect of solving the dual problem, although again we're not solving the actual problem, is that we're getting lower bounds, and that's when we do find feasible solutions, this gives us information about how close we are to being finished. So it's useful. But why even bother with a dual function in the first place? It's easier. That's the thing. When we're doing this relaxation, we relax complicating constraints. Constraints that take two blocks of a different problem. And there's just this one line of constraints here that's connecting these two parts of the problem, and that's really not allowing us to see these problems separately, and that's causing a problem. We relax it, we bring it to the objective function, and now we're solving two independent, smaller problems. So that's the motivation of actually bothering with this dual function. And what's going on geometrically is what I showed you here. So the name of the game for the rest of the lecture is how do we use this subgradient information to maximize function. Now, if the function were smooth, we have tons of algorithms that we know for, we already know this thing is concave or convex. So can you think of the simplest algorithm out there for, come again, Adrian? Gradient ascent for a concave function. Compute the gradient, that tells you the direction of most rapid increase, go in that direction. And there's a bunch of tricks about step sizes that you can do to optimize this method. Exact same idea here. What's the problem in this situation?
There's no gradient.
It's non-differentiable function. It doesn't have to be differentiable. So that's why we're going to look at a generalization of the gradient, which is the subgradient. Okay, so what does the gradient give you? So we know the way to interpret the gradient inequality is that the gradient gives us a first order approximation of a function around the point x, and you're really close to the function if it's a differentiable function close to x, but the important thing is you also get an entire support of the function. So a linear function that underestimates f of x for any x. And another way to interpret this geometrically, if you want to be thinking in terms of a convex function, is that so in this case the direction of increase is here, so you also take the -1 vector, and this vector now in the space of x and f of x, so thinking of this as an entire set, a convex function, another way to define convex function is that its epigraph is a convex set, and this gradient is normal to this convex set. Now this idea will generalize for non-differentiable functions. So this is the definition of a subgradient. It's a vector that if I walk, it's a vector that defines a hyperplane that if I stay on this hyperplane, globally underestimates my function. So it's a vector G that if I move away from x and go to another point y, but I'm staying on this hyperplane, then no matter what y I move to, I'm always below f of y. It's a definition, so f doesn't have to be convex, but the important thing for convex function is we know this G exists for every point. For a non-convex function, even if we were given a subgradient, we wouldn't have ways to verify if it is one or not. So here's a graphical illustration of what's going on. When the function is smooth at a certain point, a subgradient coincides with a gradient. If you want to think of this geometrically, the image to have in mind is the following. I'm looking for slopes that if I move along the line and I wiggle, I'm always staying under the function. If the function is smooth here and I wiggle this line slightly, but I'm always pinned down at this point, I'm going to cut in from this side. If I wiggle the line the other way, I'm going to cut in on the other side. So when the function is smooth, there's only one subgradient, it's the gradient of the function. But here, it's maybe a bit hard to tell, but there's a kink here. So what I intended to draw, but maybe it's not entirely clear, is that it's increasing smoothly, well, maybe like that, and then there's a kink. So here, wiggling within this range always results in a line that if you walk along this line, you're staying under the function. So in this case here, next to, there are many options for subgradients, including G2 and G3. And here are a couple of rules. So, and we'll see a few of these also later. And so G is a subgradient of x, of f at x, if this vector supports the epigraph. This is just generalizing this idea for a non-differentiable function. And it's a subgradient if this hyperplane is a global affine underestimator of the function. An important thing that to remember is that if the function is convex and it's actually differentiable at a certain point, there can only be one subgradient. And again, the motivation is that you can't wiggle around this hyperplane without cutting into the function. Okay, so in our case, the usefulness of defining the subgradient will be algorithms for non-differentiable optimization. So here's an example of subgradient for a max function. Again, when we have two functions, f1 and f2, and we're taking their maximum, because and f1 and f2 are smooth functions, if I'm at a certain point x where f1 is greater than f2, then the subgradient of the max function is the gradient of f1, because f1 is a smooth function. If I'm at a point x where f2 is larger than f1, the subgradient is the gradient of f2 because f2 is smooth. But if I'm over here, the subgradient is any vector between the slope of f1 at that point and the slope of f2 at that point. I can wiggle around this hyperplane and always stay under the max function. Okay, so we have a definition of subdifferential is the collection of all subgradients of a function at a certain point. So over here, what's the difference? What is a subdifferential at x0? What is subdifferential at this point here? Just the gradient of f2. But over here, at x0,
or the gradient slope between slope of the gradient of f1
at x0 and f2, including those two. So it's a closed convex set. What Leopold just said, it's this thing here. Well, at least for one-dimensional x. So subdifferential is a collection of all possible subgradients at a point. Yeah.
So this is a set of functions. What does it mean to be convex to a set of functions? In 1D, it's like the segment of slope.
Right. So that's why I'm saying if it's a one-dimensional function, this is well defined. But in the general case, what you have is the convex closure of this set here. This defines the convex closure. We'll see that in a minute. Again, a closed convex set. Okay. So, useful information for convex functions is that if we're in the interior, in the relative interior of the domain of a convex function, we know that a subgradient exists. And again, if it's differentiable, then it has this unique, the subdifferential is just a unique element. It's the gradient of the function at that point. So here's an illustration. The absolute value function. As we're moving from negative x's, it's just the slope of the line coming down, so -1. So what I'm plotting here is in the y-axis is the subgradient, and the x-axis is it's the argument. Then when we're to the right, it's 1, and when we are hitting the origin, we can wiggle between -1 and 1 and always stay underneath the function. The bottom line is that the thing to note is that this is a convex closed set. So anytime you're looking at the subgradient of a subdifferential of a convex function at a certain point, it's closed and convex. Computationally, maybe that's useful because when you have two trial directions of movement, taking their convex combination guarantees to you that you're again looking at a subgradient. Okay, a couple of useful rules for subgradients. So I've mentioned this 3 or 4 times already. If we scale a function by a positive scalar, then the subgradient of the scaled function is a times the subgradient of the original function. If we add up 2 functions, and these rules are all the same that you've encountered for gradients. So if we add up 2 functions, their subgradient is the sum of the subgradients of the functions. Affine transformation. So if I compute the argument of, if I have an affine function of x and I hit it with f of x, then the subgradient of this resulting function is given as such. And this is what we've already really seen geometrically. So the subgradient of a function at a certain point is the convex closure of for finite pointwise maxima. The subgradient at a certain point is the convex closure of the subgradients. So for example, in the case of the absolute value, this is the max of minus x and x. So at this point, both of these hyperplanes exactly approximate, exactly evaluate to the function. So this guy's subgradient at this point is -1. This subgradient is 1. So the subgradient at this point is the convex closure of these 2 points, which is exactly the interval -1, 1. Okay, another example of that in higher dimensions is the L1 norm. So the L1 norm, you can think of it as, for example, in 2 dimensions, you can think of it as 4 hyperplanes coming and meeting at the origin. Anywhere away from the origin, only one of, and I can try and draw this maybe. This is very heroic what I'm trying to do. Yeah. I always, maybe my, yeah.
On the previous slide, do we need a union in the definition?
Convex closure of, yeah. Otherwise, what would?
Okay, is the union part of the union?
Right. That's all. It's just connecting points and taking their convex costs. Okay, so maybe drawing it is too heroic, but L1 norm illustration is we have 4 hyperplanes meeting at the origin. If you're anywhere away from, well, if you're just sitting somewhere where only one of the hyperplanes is active, the subgradient of the L1 norm is just the subgradient of that hyperplane. If you go to a point, for example, 1, 0, where 2 hyperplanes meet, they are both active. They both exactly evaluate to the L1 norm, so the subdifferential is their union, and then the most sharp point is the origin. There, and the geometric intuition here is that the bigger this set that you see, the more you can wiggle the hyperplane underneath a convex function. So for example, when it's just a single point, there is only one slope that will cut the function from underneath. But at the origin where all these hyperplanes meet, you can wiggle around a lot and still under-approximate the function. Okay, another suggestion of Matthew's that I'm following, which kind of violates my aesthetics, but maybe I'll get used to it, is important stuff. So, who feels like me about this? Right? Okay. Who likes this? It's good for pedagogy. Yeah. Okay. Okay. So it's democracy. We have a tie. This is going to be useful for Monte Carlo simulation of subgradients in value functions in stochastic programming. So if we have a function of some x and a random variable, and we're taking the expectation of that function with respect to the random variable, we know that the subdifferential of the resulting f of x is just taking the expectation of the subgradients of f of x comma u. This is useful computationally for the following reason. When we're thinking of two-stage decision-making under uncertainty, you can think here of x as your first stage decision. By now, probably in the training sections, you've learned that value functions, which is the expected cost of the second stage, are convex functions of x, the first stage decision. Well, but what is a value function? It's really the average of a bunch of things that could happen in the second stage. So we can think of it in these terms here. Here's the random input of what could happen in the second stage. So we know that this function is a convex function of my first stage decisions. And if I am considering a certain trial first stage decision, a good way to compute its slope, not exactly, but a good approximation, is to simulate a bunch of second stage things that could happen, and calculate the slope of the cost for each of these second stage things that could happen, and then average them. That's what's being said here. So you generate a bunch of samples of randomness, you optimize your second stage against them, and then you average them up. It's going to give you a slope. It's not going to necessarily be an exact slope, but it'll be close. So a lot of Monte Carlo-based simulation methods for stochastic programming are based on this idea. Is this making sense? Okay. This is quite useful. We're going to use this. Okay. Another important piece of information is that, and again, this comes up in the L-shaped algorithm, is that when we're solving a convex optimization problem with a convex objective and convex constraint functions, the dual optimal multiplier is, well, minus the dual optimal multiplier, is a subgradient of this function g of y. What is this function g of y? This is a mapping of how my objective function changes as I am changing the right-hand side. Why do you, this is kind of maybe premature to ask, but can you think of how this could be useful in a two-stage stochastic programming context? And one hint about that is that the general form of the program is something like this. And when we are doing second stage optimization for a given trial X, what we're doing, we're moving the Tx to the right-hand side. So basically, the value function is an average, is a convex function of X. And by applying this theorem here, what we're being told is, in fact, the slope of the value function is the dual optimal multiplier of just the second stage optimization problem. This is how this is going to come up in two-stage stochastic programming. I try a certain x, I bring the tx to the right-hand side, I solve this linear program only with respect to y. The dual optimal multipliers, they're the slope of the value function at that point x. So you can already see how this is going to be set up. What we're going to be doing, this is a preview of the L-shaped algorithm in very simple terms. And a two-stage stochastic program is really the following. First stage cost. I'm looking to decide what to do with the first stage decision that I'm making. First stage cost and some convex function of first stage decisions in the second stage. It's some convex function. We don't know what it is. But what we can do is the following. Try a certain x. I know how much that will hurt me in the first stage. That's just C transpose x. But when I also solve the second stage problem, I have an idea of what the second stage value function will be. I'm minimizing the sum of the white and the yellow curve. I don't know what the yellow curve looks like, but every time I consider a certain candidate x, I get a slope. Then I move somewhere else, I get another slope. So this thing, I don't know, but I'm going to start getting a bunch of linear approximations of it, and a good fit to the second stage value function will be this piecewise linear thing. So I'm going to be trying different x's, moving around based on the subgradient information, and minimizing the sum of this piecewise linear thing plus the C transpose x. That's how this is going to come up in the L-shaped algorithm. Okay, another rule. Sorry, give me 1 second, take out my watch so I keep track of time. Okay, composition. So, F is a composition of H and a bunch of functions F1 to Fk to compute a subgradient of F at a certain point. What I can do instead is compute subgradients of F1 through Fk, compute a subgradient also of the H function at that point, and take their inner product. And this is just a generalization of what you already know from gradients. And it's a fairly simple proof that you can verify. The requirement here, however, is that H is a convex, non-decreasing function that comes up in the two inequalities here. You exploit that in the proof. Okay. This figure starts giving you hints about how you can use the subgradient information to maximize a convex function. The geometric by definition, a subgradient is a vector G that satisfies this inequality. The important thing from the definition is the converse implication. If I am at a point y where the function f is less than its value at a point x, then this inequality must hold. So the subgradient at x transpose with y minus x has to be less than or equal to 0. There is geometric information in this inequality here. What does it mean for these two vectors to they have an acute angle, obtuse angle between them. So if G is pointing one way and you want to decrease the function, you've got to turn around and move in the other direction. That's the geometric information that is here. The one thing you know is that if you move anywhere in the half space that G is pointing to, you will never land in a new point where f is less than what it already is. So if you have any hope, it has to be in the opposite direction. And here's an illustration. So in this case, at this point x1, the function f is smooth, so there's a single subgradient, which is the gradient. And it's actually the direction of steepest ascent of the function. Here you have an entire subdifferential, which has more than one element, and you want to definitely be taking a direction that forms an obtuse angle with any of the vectors that lie in that range over there. So, you know, the cookie is somewhere in here, basically. That's where the function is less than what it is currently at x0. Okay, that's in words what I just described. Okay, and the last part before the break that I want to discuss is when to stop an algorithm, a subgradient algorithm. So we know from convex differentiable functions that a necessary and sufficient condition for a non-constraint problem is that I'm at a point of zero slope. If I'm not, I can move around slightly, decrease the value of the function. The idea is the same in non-differentiable optimization. But now the thing now is that since I'm looking at a non-differentiable function, I don't just have a gradient, I have a whole subdifferential set. So the necessary and sufficient condition for optimality of non-differentiable optimization is that 0 belongs to the subdifferential set. Now, the geometry is very simple to interpret. The problem in practice is that we will have algorithms that return subgradients at points, and these algorithms will behave to some extent randomly. They will give you back a subgradient, but they won't give you the full subdifferential of a function at a certain set. So you're going to only be lucky if you get back 0 as a subgradient from an algorithm. If you do get it back, if you ping a certain function, ask it what is a subgradient at this point, and it returns back 0, then you know you're optimal at that point. But it's not like you can really rely on that, because there's going to be more than one candidate that will be valid subgradients at that point. Okay, and the proof of why 0 being a subgradient is equivalent to optimality, just follows from the definition of the subgradient. Okay. The geometric intuition behind this is really simple, but it can lead to some interesting insights. So when I'm doing piecewise linear minimization, what do we know already about the subdifferential at a certain point? Or let's think of when is this function minimized? Is it a convex function? First of all, obviously. It's minimized at a certain x star is equivalent to if I ask for the subdifferential set of that function at that x star, 0 has to be a member of that subdifferential set. We saw this in subgradient calculus. You can also think of it intuitively, geometrically. What is the subdifferential of this piecewise linear function at a certain point? When I'm looking, for example, at the absolute value function, and I'm here, I don't care what the subdifferential of this line is at this point. It's not active at x. So when I'm looking at a piecewise linear function, I want to be basically looking at all the lines that are active at a certain x, and I take the convex closure of their subgradients. The subgradient for an affine function of x is the coefficient. So what I'm looking for in this situation for optimality is that those affine functions that are active, 0 has to be within their convex closure. Another way of saying that, if 0 has to be in their convex closure, I can certainly find a bunch of lambdas that sum up to 1 and hit each of the coefficients ai with one of these lambdas, and that has to evaluate to 0. But only for the hyperplanes that are active. So what I just said in words is basically that these conditions have to be satisfied. Lambda I is 0 for non-active hyperplanes, and I can take these lambdas non-negative, they sum up to 1, and their weighted combination of them and the AI is 0. That's actually the KKT conditions of the same problem written slightly differently. And in fact, if you were to solve this problem using the best possible method, you would not solve this problem using the subgradient method. It's just a linear program. So you can formulate it in this form, which is equivalent, and tackle it using linear programming. But the insight that is relevant here is that the KKT conditions of the dual of this problem are exactly the optimality conditions over here. So although the observation is very simple, that 0 has to be a member of the subdifferential set, you can get non-trivial conclusions from it. Okay, we also have optimality conditions for constrained problems. And as you would probably guess, since we haven't really seen any departure so far between differentiable and non-differentiable optimization, is that the conditions generalize for the KKT conditions generalize. So do you recall what the set of KKT conditions were for a convex optimization problem? 4 things. Very, very useful and very annoying to remember. It's the two feasibilities, primal dual feasibility, and two more. Right, so the gradient with respect to x of the Lagrangian vanishes, and
gradient of the objective function times the sum of the dual multipliers and the constraint equals 0.
coming in.
Gradient of the objective function plus the sum of the dual multipliers and the gradient of the constraint is equal to 0.
That's what Leopold just said, that the gradient of the objective is parallel to the linear combination. Another way to think of that is that the Lagrangian function, its gradient with respect to x is 0. And there's the fourth one, which is up on the slide. Sorry, complementary slackness. So we take a constraint, its product times the dual optimal multiplier has to be 0. If the constraint is active, the lambda has to be 0. If the lambda is non-zero, the constraint has to be non-binding. Okay, same thing with constrained optimization of non-differentiable functions. It's just that now we have to be thinking in terms of subgradients instead of gradients. The rest remains unchanged. Primal feasibility, dual feasibility, what Adrian and Leopold just mentioned, and complementary slackness. So finally, we enter algorithms. Okay, so I'm gonna present to you the subgradient method, and the key there, I mean, the geometry, we've kind of seen it already. The engineering creativity comes in designing proper step sizes. And we'll see a couple of ideas and why they work. And then I touched on this already in the beginning of the last hour, but we'll see how this is all relevant to stochastic programming. We will actually see the proof of the proposition that I presented to you in the preview last hour. And finally, some tricks for optimizing the step sizes, and also how the method will be used for constraint non-differentiable optimization. Okay, so this algorithm should look quite familiar to you. It's the steepest descent method applied to non-differentiable optimization. It's quite entertaining to watch Stephen Boyd's video on this lecture, because he's really emphasizing how stupid this whole thing looks. It's extremely simple, and it is also extremely slow in convergence. So when you can get away with an algorithm that is not a subgradient method algorithm, it's preferable. For example, earlier when we saw that piecewise linear optimization, we could get away with a linear programming reformulation. You should go with that anytime you can. The motivation of why we're going with a subgradient method in our case is we don't have much of an option, since we're trying to decompose problems. And there, once we decompose, the dual functions we get are non-differentiable. We're stuck with methods that are somewhat slow. Okay, now one of the reasons that Boyd emphasizes that this is a non-promising approach is that, as opposed to the in the gradient method, what guarantee do you have, assuming you can make the alpha as small as you like? Come again. In the steepest descent method, what guarantee do you have about progress?
Slowly.
When you're looking at step k plus 1 and comparing it to step k, there is something you're sure about.
Yeah, it's decreasing.
You're decreasing. I mean, if you choose the alpha to be small enough, you definitely can decrease. Not so in the subgradient method. there are situations when you're sitting at edges of functions where selecting some subgradients can move you, and taking the opposite direction, can actually move you in what will result in an increase of the function. And there is an example in Boyd's slide that shows this for the L1 norm. So you have other guarantees from step to step, and we will exploit them in the convergence proof, but not necessarily that you're decreasing the value of your objective function at any given step. So given that this is the case, one thing you definitely want to embed in your code is keeping a memory of your best value so far. And we're going to use this best incumbent in the proof that's coming up. Okay, so this is the algorithm. We are at a certain point. We compute the subgradient of the function at that point and move in the opposite direction. And that's our new point. Another reason that Boyd rants on and on about how stupid this all looks is that you fix the step sizes in the algorithm ahead of time. And that's somewhat true. In my experience, for example, during my PhD, one thing I did that paid off was when I was far away from optimum, my step sizes would be large. But then when I got around the maximum, if I was moving around too much, I would never hone in. So after like 50 iterations, I would jump in manually and decrease, or I would embed that in the code. But you can do tricks to make this smarter than just fixing step sizes in advance. But the truth is that there's a lot of calibration involved. So here's a couple of options you can try. You can go with constant step sizes, so constant alpha in advance. Constant step length, which will guarantee that the norm of the vector of your jumps is always going to be equal. Square summable step sizes, but not summable. So this is square summable, but not summable. And the special case of this is non-summable diminishing, but non-summable. So each of these is an option. Each of these will give you different guarantees about how close you land to the dual, not how close you land to the dual optimal x, but how far you are going to be from the objective function, optimal objective function value. Okay, so here's the assumption we're going to use for the proof, and it's important to remember the notation here. So f star is going to be the optimal objective function, the objective function value at the optimal point, and we are going to make this kind of Lipschitz assumption about the gradient. So the norm of the gradient cannot be greater than a certain bound, capital G. And we are also going to assume that we have an upper bound on the distance of how far we are at the starting point from the optimal point. This can be tricky sometimes in some problems, but usually you can come up with a really crude bound. So the assumptions are stronger than they are needed for the proofs that are going to follow, but that's just to make the proofs short enough. So here's the preview of the results, and all of these conclusions are going to drop out of the same inequality. It's just that depending on what step size we choose, we get a different guarantee here. So the F bar that we converge to, in case of constant step size, we have this guarantee here. Constant step length, we have a guarantee over here. And for the diminishing step size rules, we know we converge to the optimal value, but it takes forever. It also takes forever in practice. So these things I experimented with, and although this is the most satisfying theoretically, it's useless in practice. It's too slow. And in fact, this wasn't bad at all, as long as you calibrated it a bit, depending on how far you were from optimal. Okay, so here's the convergence proof. So we can't, based on what I told you earlier, what can we not use as our Lyapunov function for the proof? If we're not sure if at every given iteration we're decreasing or not the objective function value, the objective function value can't serve as our Lyapunov function. So as the function, what I'm referring to as a Lyapunov function is a function that when we apply an iteration of our proposed algorithm, we know that this function will decrease a bit and eventually will converge to 0. What we will use as our Lyapunov function is how far we are from the optimal x star. We don't know where it is, but we will provide a guarantee that at every given iteration we're getting closer to it. So although we might be getting worse in terms of objective function value from step to step, we have a guarantee that given an alpha small enough, we're actually getting closer to the optimal x star. How we get that guarantee is by exploiting the subgradient inequality. So here is how we establish that. Our distance at k plus 1 from x star is equal to this by how our algorithm works. We take the sum of squares here, so we take this term and this term as 1, and then the rest on the other side. And here we use the subgradient inequality. So what we know is that gk is the subgradient at point xk. Let me write it out. The way we're exploiting the subgradient inequality here is that we know that the f at the optimal x star is going to be greater than or equal to the f at xk plus gk transposed moving to x star from xk. This is what we're using to go from here to here. Is that clear? Okay. It's already here. Sorry. Okay. So now we're looking good. We have what terms are helping us here. So we would like this to be as small as possible. So basically, this term is helping. This term is hurting us, but it's step size square, and we're going to exploit that. So this is what we just derived earlier. We have a bound on the distance to optimal x star, the capital R. And what we've done here, actually this is not what we derived earlier. What we are doing here is we're repeating this inequality over and over. So once we establish this inequality, we play the same game again for this term here and again until we hit x1. So what we're going to get here is a sum of these terms over alpha I, and the sum as well over here, and that's the inequality we get over here. Then we can bound the norm of the g's by capital G, and we can bound the distance of x1 to x star by capital R. Here what we do is we, why does this hold? Yeah. Yeah, it just holds by the construction of f best. It's the best, the lowest f we found at any given iteration has to be lower than the f of xi from I1 to k. And since we know that this, which is really what we're interested in, is upper bounded by this, we've found a ceiling for this guy. This is just this here. We found a ceiling. If we bring it to the left-hand side, we have this upper bound r squared plus g squared, the sum of I squared, and this is where we arrive at. So we have this upper bound on the objective function value over here, and this is where we're now going to play these different games on step size rules to get different bounds depending on what approach we apply. So, for example, constant alpha, all we do is we take the alpha i's, plug in the constant alpha that we're using. This is what we get, so each of these terms is the same, so we get k alpha squared and k alpha over here. As we're pushing k to infinity, this fraction converges to g squared alpha over 2. Okay, that's for constant alpha. Probably going to be a lousy theoretical bound given the lousy nature of capital G. And for constant step length, again, looking at the, we have, this is the inequality we derived. We have g squared alpha squared is upper bounded by gamma squared. Upper bounded. Oh, no, sorry, yeah. Yeah, the G here is a lower bound, so this cancels out with this, so we get the term over here. The same thing goes on over here. So again, as we're pushing the k to infinity, this gets simplified to g gamma over 2. And finally, you see why this really small step size rule works. The numerator becomes something finite. The denominator goes to it becomes unbounded, so the ratio is 0. The message from the proof is not so much the bounds as it is the guarantee that we can always be getting closer to the x star. That's the geometric intuition you should have about the algorithm. Now, these are nice theoretical derivations, but how do you actually make it work in practice? Before talking to you about some ideas for specific step sizes, I want to talk quickly about the termination criteria. What would you do if you what I can tell you and what you're going to encounter in the exercises is you will have a black box that gives you an f of xk and a g at a certain point xk, so a subgradient. What could you think? And you can keep track, keep memory of the progress you've been making. So what can you think of as a good termination criteria?
If the successive subgradients tend to 0?
Yes. That's the problem, is you can be, even at the let's think of the absolute value function. Your machine can turn anything here. It can be really far. It can be as much as it was all the way to get down here. So it makes sense what you're saying. And indeed, if you actually get 0, you know you're spot on, but it can work really bad. The question is basically open-ended. Like, I can't think right now necessarily of, in the generic situation I'm describing to you, I can't think necessarily of a great termination criterion. Maybe what I would do is measure the distance of my jumps. Well, but then again, that's controlled by my step size. You could maybe keep track of the progress you're making in the objective function value. That's not necessarily a bad termination criterion. The one we are going to use in stochastic programming is quite different in flavor. We will be getting, think now of minimizing two-stage stochastic programming. We will be getting at every step from the dual function a lower bound, since we're minimizing. And we will, by the optimization of the Lagrangian function that we will be doing, we will be getting a primal infeasible point, but it's going to be slightly infeasible. So we will be tweaking that around a bit to get a feasible point. And that will be giving us an upper bound to our optimization problem, and that gap is a guarantee of optimality. When it becomes small enough, we stop. That's going to be the idea in what we will be doing. Okay. Yes?
But if the gap is bigger than our tolerance,
yeah.
the gap is bigger than the tolerance.
That's bad news. So you are either your feasibility recovery technique sucks, or you are not making fast enough progress with your subgradient algorithm. You should be maybe more aggressive in your step sizes. Here's another question for you. Suppose I get 50 iterations in a row where f best k is increasing. Am I happy or am I concerned? The reason being, I could be in the other end of the world and making progress by doing like 1 meter step at a time. Yeah, locally I'm making progress, but 50 successes in a row really means I'm moving slow to the optimum. What you want to be seeing is that, and who's to say, if it's 50 in a row, it could be 5,000 in a row, and you could be waiting forever. There's a bias there. Obviously, you are making slow progress. What you want to be seeing is that you are making some initial progress with the subgradient steps, but at some point you get a decrease. Why? Because you've reached around the cookie and you're overshooting. When you overshoot, you get an F that is worse than your F best so far. So that's some things to pay attention. Then again, on the other hand, if first iteration is a decrease, that's alarming because you really overshot. Even in the first jump, you went from one end of the dual, multiply universe to the other. And the function actually dropped because you were so aggressive. So what you want to be seeing is a bit of progress and eventually a slight jump down. And yes.
And what about line search for that? Adaptive.
Right. So there is the notion of line search, and now you want to be thinking of you can do it. Definitely, you can do it. So there's a variety of tricks you can play, and line search is one of them. Any trick you want to come up with, however, be cautious of the fact that just the computation of f will be a bit expensive, if not quite expensive. So that's something to keep in mind, because each computation of f is really solving a bunch of scenarios in our case. And it'll hurt a bit. So the acceleration you gain by being smart with your step size, you might lose it by just coming up with a step size. These are trade-offs to keep in mind. And okay, so that's about termination criteria. Thought I wanted to say something more, but slipping my mind. Okay, we saw this slide already. So this is our generic two-stage stochastic programming framework, which motivates this whole thing. And the proposition I mentioned earlier is that I take the Lagrangian function, I compute the x that optimizes the Lagrangian function at the current lambda and the current nu. I claim that the violation of that constraint, the ax0 minus b and the cx0 minus d, is a subgradient. First of all, silly sanity check. Does it have the right dimensions, this vector? It's as these guys are as many as the lambdas, and these guys are as many as the nus. So we're looking at a properly dimensioned vector. The claim is that it's the in our case it's a super gradient. Yeah, it's a super gradient, which means in fact that no, this is correct. This is the correct inequality here. So let's prove that. By the way, why is this good news computationally? What is going to be your subgradient algorithm in the case of two-stage stochastic integer programming, given what I told you? Take your current lambda nu, optimize the relaxation. The direction you move is just ax minus b, cx minus d. You just look how much you violated your constraints, moving the opposite direction. So you get the direction of movement for free. You get the dual function value, which is your lower bound, but you're also told for free where to go. That clear? That's really why we're bothering with this idea. Okay, so let's prove the proposition. So I'm going to use this x star to denote the optimal solution given a lambda and nu. So what we're doing here geometrically is we are at a certain point lambda 0, nu 0. Yeah. And the best x corresponding to these multipliers is x0. We're going to move away from lambda 0, nu 0 to a new lambda nu. We want to make sure that this hyperplane here is over approximating the dual function. Okay. So what we want to show is this. So we start from the right-hand side. ZLR is just the Lagrangian function value at lambda 0, nu 0. Okay. How did I get this here? That's just the definition of the Lagrangian function at point lambda 0, nu 0. So basically, the Lagrangian function at this dual point is that function evaluated at the best x. What is the best x? It's x0. So it's this, and if I plug that into here, I am left with this stuff over here. Okay. And now the claim is that this is greater than or equal to this. Why is that the case?
Because it's 0,
the best response to lambda nu is when I'm optimizing the Lagrangian function, which is at a point lambda and nu, the best reaction is x star. So when I'm trying out x0 instead of x star, it's a suboptimal primal vector for this optimization problem here. That's where this inequality is coming from. Given lambda nu, given if that's the relaxation you want to give me, then I can do better than x0. I can go with x star, which is the best reaction to that. And that's just this is just a Lagrangian function value at lambda nu. So indeed, this inequality follows. Okay. Takeaway is what I told you earlier. We get the dual function value for free, but we also get a direction of movement.
The direction
Yes.
is a complete plane in the space because it's ax minus b and cx minus d, but a combination of these two.
What you want to know is what? How would you implement the algorithm in code? Suppose I give you alpha equal 0.2. You want to come up with a new lambda and a new nu. So I'm not sure what you mean by combination, but what you do in terms of code is your new lambda is your old lambda minus 0.2 times the vector you plug in here is ax minus b, not cx minus d. And for the new part is the cx minus d. Again, remember you're now moving in the dual value space. But in fact, the primal constraint violations are telling you where to go. This is intuitive a bit, if you think about it. Let's think of ax minus b for a moment. So let's think of what's actually happening. Okay, so suppose for a given the ZLR is minimized. Okay, what we're doing at every iteration is this basically. And let's forget the equality constraints. Let's just think of the inequality constraints. For a certain lambda k, suppose I get an xk that violates the ax minus b. Intuitively, what's going on here is you're saying, okay, I won't satisfy it, but I'll get hurt for violating it, right? Because here, I hope I'm writing this right. Yeah, good. So if I violate this, this term would become positive, and if my lambda k is positive, which it has to be, I'm gonna get hurt a bit. But I'm still gonna pick an xk that violates it, because when I'm trading off also the contribution from C transpose x, it pays off to violate it. And so now suppose that this axk minus b is positive. What's gonna happen next round? What is lambda k plus 1 gonna look like compared to lambda k? Remember that for the supergradient algorithm, we are going in the direction of the supergradient, not the opposite direction, because we're maximizing the dual function now. So it's plus alpha. So basically, this is just a disciplined and theoretically backed up way of slapping your hand. That's really what it is. Okay, you violated it. I'm going to hurt you more in the next iteration. Do your best, again. Maybe you're going to decide to violate it again, and then I'm going to slap you even harder. That's really what's going on here. It's just that we also have a bunch of theory around it to make sure it converges. It's really intuitive if you think about it, what's going on here. Well, how much are you going to slap me? Well, that depends on the step size. I'm going to choose, and we have all the guarantees we saw earlier about how strict to be. Okay, is this clear? This is really helpful. This is also very helpful to remember when you're debugging. It helps. Okay. I talked to you about a bunch of bounds depending on step sizes you can use. I'm going to now give you some practical rules that I myself have used in the past. So here's a nice step size rule. This one I used in my PhD. So the idea here is that you have the step size be equal to the distance from f star divided by the norm of the current subgradient. What's weird about this one? Think about having to implement this. There's something here that is a bit circular. Yeah. But, for example, in my case, it was the operating cost of California electric grid for a day. Okay, I didn't know if it's 5,250,000 or 5 million. Matters in practice, but I could plug in a reasonable lower limit. I put 5 million. So you don't know exactly most of the times, but depending on the nature of the relaxation, you get some experience and you can come up with a pretty reasonable F star. Now, what is this doing geometrically is the following. It's basically if this is your convex function that you're optimizing and you are at a certain xk, suppose you knew the f star, even if you don't know it, suppose you're using an f star like this. Geometrically, what this step size is doing is it's saying, okay, I don't know what the f really is, but let's suppose that it's exactly approximated by this hyperplane here that I've just computed because I've gotten the GK. I know what this hyperplane that supports the function looks like. My God, my drawing is really bad. So let's suppose that this is really my function. I'm going to pick an xk1 that brings me to the f star as if my function were affine. linear plus constant at this point. It's not, but let's suppose it is. Where would I go? I would go here. So here's a couple of remarks. If you have a quadratic function, how much progress are you making at each step? Very intuitively speaking, you're cutting your distance from optimal to half at every point. If you have a piecewise linear function, you get finite termination, because every time you're just snowboarding down one of the slopes, you hit a crease, you snowboard down a different slope, you hit a crease, and eventually there are finitely many such slopes, you land in the bottom. Typically, by the way, our functions will be piecewise linear. It's just that there's so many slopes that, in theory, it's finite termination. But yeah. Okay, so that's the geometric intuition behind Polyak's step size rule. Here's how you come up with the idea. You start with the original inequality over here, and what you ask yourself is, how am I going to make this? Really, what I want to be doing is getting this as close to 0 as possible. So how am I going to pick my alpha to make this as close to 0 as possible? I'm going to minimize this thing viewed as a quadratic function of alpha. Does that make sense? Make sense? Okay. So to do that, you just take the gradient of this thing with respect to alpha, set it to 0, and that's your step size. Okay. This is really useful in my experience. It works really well. One of the reasons it works well is that everything is calibrating itself in this situation. So even if the slope of the function you're optimizing is changing from iteration to iteration, the alpha is adaptive. It's going to follow those changes. Whereas with a constant step size rule, for example, the geometry might be really weird in some parts and be more flat in other parts. Okay, so what we get then is a proof that this step size rule converges to optimality. And what we do is pretty similar to this trick we did earlier. So we plug in this step size and we get this upper limit. So that just comes from over here, right? If I use this alpha and plug it in here, this is what I get in the right-hand side. I can play this game over and over until I get to x1, so you get this telescoping inequalities. So you apply it again here and so on, and you get a summation over here that looks like this. You bring that to the left-hand side, so you get this upper bound, which is r squared. Now, since I know that this sum is upper bounded, if I take the limit to infinity, it's a finite sum of non-negative terms. It has to be the case that the series is converging to 0, which establishes basically that by using the step size rule, the f of xi will go to f star. That's clear. Okay, so for me, the most useful, and probably I should have put this little attention sign also over here. This is probably, in my experience, the most practical step size rule you can use. There are a couple of other ones that Boyd mentions in his slides, but I've never tested, so I don't really have an opinion. What is the intuition behind this one over here?
to add some inertia.
How do you mean inertia?
Well, since we use the last step,
Right.
as
You trust that.
yeah,
You trust that
I don't
direction.
want to change too much.
Exactly. Exactly. Very similar flavor over here. So I'm just building up trust on this S vector based on what I've been doing previously. The trust I assign to my current estimate of the subgradient is 1 minus beta. The trust I assign to what I've built up so far is beta. So the S is a linear, is an affine, is a convex combination, sorry, of the two. Okay, and the step size rule is just Polyak over here. Now, Boyd mentions it as a side note, but the truth is that there's an enormous family of other methods beyond just simple vanilla subgradient, and Yuri Nesterov has done plenty of work on this. You have bundle algorithms, you have cutting plane algorithms. You can get really creative about what you do. For example, one thing you could try is, you know you're getting this for free, right? At every iteration. You get the G, which is the slope of this thing, and you're also getting the F at that xk. One idea is that and that's I think that's the trust region. No, that's a bit different in flavor, but the idea is the following. You create, from all the iterations you're doing, you create an objective function term that is taking this piecewise linear maximum of this, which is a reasonable approximation of the function you're optimizing, plus a bunch of penalty terms. The penalty terms can penalize how far you well, what the trust region does, oh, it's not mentioned here, in fact. Anyway, you have variations like that. The problem with a lot of these methods is that when you are working in large dimensions, in high dimensional space, they suck. Because you really need many, when you're working, for example, we have a problem that's 40,000 dimensional space. Okay, yeah, if I'm doing this trick on one-dimensional function, it's going to work really good. Pretty fast, you're going to get a really good approximation of your function. When you're working in 40,000, you can already see the trouble in the one-dimensional case. Suppose that my x is unbounded. Where would I go if I were optimizing just the cutting plane approximation of this function? I would go to the limit, which is minus infinity in this case, if I'm minimizing. If I put a lower bound, then, and this is the function I'm optimizing, I would first move from x0 to x1. Then I would create a cutting plane here, so finally I would land somewhere over here, and then things would start getting interesting. Now if we are living in a 40,000 dimensional space, you're going to visit all of these corners before you even get started with making some progress. So it really fails. And then you start getting creative with adding also other stuff except for the cutting plane approximation of the function. Okay, I think I expanded on that enough. Now, projected subgradient method, and this is the last, I believe, slide, well, almost second to last slide of the presentation. What I showed you so far, right. I never talked about, I just showed you a way for optimizing a convex function. So I never talked about constraints on the x's. In the relaxation of the stochastic integer programming problem, for example, we do have a constraint. What is it?
Remaining
Come again?
remaining constraints. If you relax them, you still have
Here's the trick. It's easy to confuse now what we're optimizing. What are we optimizing in
the dual.
the dual?
Okay.
So the primal constraints non-exist anymore. We're in the dual space. But
The lambda.
exactly, the lambda is non-negative. So it won't work just as I presented it to you for the dual function optimization. So one algorithm you could apply is, well, what's the simplest thing you can think of?
All negative entries.
Exactly. That's what you've just done is really a projection, basically. So that's the exact idea. It's simple as that. You do your subgradient update. If some of your entries are negative, you floor them by 0. And that's the projected subgradient method. Now be careful, projected here refers to projecting the new vector you have to your feasible space. It's not talking about projecting, for example, the subgradient itself. You take the new vector, you project it to your feasible space. This thing will also converge given proper step sizes, and the way you prove that is basically the projection. If you remember what our metric of progress was in the proof of convergence, was the distance to x star. The subgradient algorithm was already helping us get closer to x star. If we now project, that brings us, it has to bring us even closer to x star in case our space is constrained. So adding this operator here, if anything, it helps our convergence proof. So the same rationale we applied earlier for the convergence proof of the vanilla subgradient method, same idea applies here. And with that, I think we're good for today. Matthew's going to throw at you a couple of exercises that you can implement to get a feel of the algorithm. And see you in a week.